Cool.
Okay, I just have 3 slides for today, and then I assume we're still, no offense, but I assume we're not good at determining if molecules are polar or not.
I don't know. What do you think?
Based on the chemical formula. Polar or non-polar?
Polar.
I say.
Yeah, okay. These are the kind of questions you eventually need to answer. So we'll practice that after. I've got a worksheet up.
Like on our tests and stuff, get like the periodic table with our molecules.
Yes. Yeah, you'll get electronegativities on the test. Yay!
Ew, take it back.
Ooh, somebody failed. No, I'm kidding. Okay, anyway. I want to cover just a few new slides, and then we'll do a worksheet practicing polarity stuff. Okay? All right, so one of the big reasons we're talking about polarity is because, Josh. One of the big reasons we're talking about polarity is because it has a ton to do with the properties of different substances. We're going to talk about some of those different properties. One of them today is solubility, which is basically, if I oversimplify it, is the ability to dissolve in other materials, okay, or the ability of 2 things to dissolve together, okay. I'm just going to give it to you straightforward, okay. Turns out, if you have a polar solvent, it will dissolve polar solutes, but not non-polar solutes. What is a solvent and a solute, you might ask? I will tell you. So if I had a beaker and I had some liquid here, that liquid is referred to as the solvent. It's the thing that I'm trying to dissolve something into. If I have another container that I am pouring in here and trying to mix in there, that stuff that is going into the solvent is the solute. Generally speaking, you have less solute than solvent, but if you have similar amounts, then it's just kind of arbitrary. You pick which one, how you're thinking about it.
So, like, you got like a real world example.
Real water example. Water would be my solvent. Sugar would be my solute that I can dissolve into the water. Okay? But turns out it matters whether these 2 things are polar or not to determine if they dissolve. We know that sugar dissolves in water, salt dissolves in water, sand does not, oil does not. There's all kinds of things that do or do not dissolve in water. And so turns out that the polarity is very important in determining that. Okay, so if I have a polar solvent, polar solutes will dissolve in it. Okay, if I have a non-polar solvent like oil, if I had a container full of oil, then I would only be able to dissolve other non-polar solutes in it. Okay, I guess I mentioned salt. That's technically ionic, which is kind of a separate topic. We're kind of just talking about covalent stuff, but salt does dissolve, so it happens to work. But some ionic things do or don't dissolve. That's a kind of a separate topic. Okay, so a common phrase that you might hear when people talk about this is like dissolves like. If the polarity matches, then it will dissolve. Some of you may be wondering, why? I will tell you. Turns out if you have, let's talk about polar solvents first. If you have molecules that are polar, they're going to be attracted to each other. Which if you stop and think about it, it kind of makes sense. If I have a bunch of molecules that have a positive and negative end, and I put them all in a container together, they're going to be attracted with the positive and negatives wanting to be near each other. Okay? And so if I introduce another material that also has positives and negatives with it, like sugar into water, the sugar has positive and negative ends, the water has positive and negative ends, and so it makes sense that they would be drawn toward each other, and the sugar would easily mix in the midst of all the water molecules, and so the sugar just moves throughout the water and they evenly mix out. If I introduce a nonpolar molecule, well, the polar molecules are all attracted to each other, and the nonpolar molecule cannot introduce itself in between those attractions very easily. Okay, you can if you like force it to mix, but it will naturally unmix itself. Okay, so anyway, this is basically a bunch of words saying what I just said. Okay, the partially charged ends are arranged so that opposite charges are near each other. This is especially true if you freeze a material, right? If you freeze water, the ice arranges itself so that the positive and negatives line up. Okay, and nonpolar solutes will not really mix in because if they did, it would disrupt those attractions. And so one of the mysterious things about the universe is that things will naturally arrange themselves in a low energy state, or they will, or low energy, high entropy. There's a whole other conversation to be had about that. Okay, but it's more stable for positives and negatives to be attracted to each other. And so you guys have probably seen this. If you dump oil into water, the oil just floats to the top and it separates. You don't even have to do anything. It just does it by itself. Okay, kind of interesting. We okay with this? Okay. Now, because the world is not as simple as we always like it to be, turns out some molecules could be classified as both polar or nonpolar. Okay, on here I say partially. Partially is probably a misleading term. Okay, but what I mean is that the molecules we've been looking at so far are very small. And so you can just look at the one small molecule and look at whether it's polar or not. But there's a lot of molecules out in the world that are way, way, way bigger than what we've been talking about. So much bigger, something like this. How many atoms are in these molecules?
They're fat.
Well, they're called fatty acids. Yes. So these atoms are much bigger, or I'm sorry, molecules are much bigger than what we've been talking about. They're like 50 atoms. How much, Fraser?
Pretty simple though.
Yeah, they're not super complicated. Oh, you counted it? Nice, 55. Yeah, I was just guessing. I guess that was a pretty good guess. Okay, so, anyone have their electronegativities memorized? You don't have to, but carbon, hydrogen, is that a polar or non-polar bond? What'd you say?
That's polar, right? Non-polar.
Carbon is 2.55, hydrogen is 2.2. Non-polar. It's a 50-50 guess, so there you go. Non-polar, okay? So this molecule is big enough that that the electrons in this area are not going to be as affected by this portion over here that's highlighted in red. Carbon, oxygen would be a polar bond. I've got two of them right here. So electrons are being attracted slightly more around these oxygens. Okay, so maybe I have some polar bonds here, but way down here on this end, these electrons over here are not really affected by that over there. So I can actually talk about different regions of this molecule as being polar or non-polar, even though they're technically part of the same molecule. Yes?
Is that only possible because it's larger?
Right, it's only possible because it's larger. If I had a small molecule like carbon monoxide, which is not exactly how you draw that, I can't remember how you draw it, but something small like that, if the electrons are drawn over here, I've got my slightly negative, slightly positive, like that's the whole molecule. But yes, when I have something as massive as that, now we can talk about different regions of the molecule. Yes?
What would the shape?
Whoa, that was loud. What would the shape be?
Yeah.
Great.
We talked about is that horrible lines, or is it?
Good question. Oh my gosh, I'm really happy you're asking about this. So yes, side note, this wasn't necessarily something I was gonna ask you guys about, but yes, this is not actually a flat straight line. When we talk about Vesper theory, we're talking about one central atom, and I'm looking at all the things attached to that part. So if we were gonna talk about Vesper theory, I would have to ask you about each carbon separately. So these electron groups, right, there's 4 bonds here, arrange themselves in a certain way around this carbon, Same thing here, or I could skip all the way here. These 1, 2, 3 electron groups arrange themselves there. So you actually have multiple Vesper shapes depending on which atom you want to call your center.
You should make that one using like the building.
Yeah, it actually wouldn't be that hard.
Okay,
If I have four electron groups, what shape is that? Tetrahedral. So, right, it's not a square, it's 4-dimensional, but it would actually just look like a zigzag, is what it actually is in real life. And then this is actually trigonal planar over here.
but like how would you?
It's the same thing you've done, it's just a bunch of them connected in one big molecule. So it seems spooky.
How
It would
you
just be
say
tedious.
it? Like how would you be like this? Would you just say like the left part
For
of
the
it?
shape?
Yeah.
Yeah,
Like,
so
would you say, like, the
it
left
doesn't
part?
make sense to talk about the Vesper shape of the whole molecule. That's not really a thing. We would say the arrangement around this atom. So this is like a tetrahedral location, I guess. I don't know. I could look up the exact wording of how a chemist would really say it. There's a fancy way to say it. But you just have to talk about individual spots. Yeah. Yes.
Are there ever like molecules that have more than 2 like polar atoms?
Sure. Yes. I mean, if you, my biochemistry is failing me. What's the molecule is it a lipid when you take 3 of these and they all bond together?
Yeah.
Yeah, a lipid. So like a lipid would have because if you have 3 of these bonded together, then you have like 3 polar regions.
No, it's
Yeah. Do you guys know how big proteins are compared to this? Anyone have any?
Way bigger, smaller? I don't know.
Proteins are hundreds of thousands or even millions of atoms, and it's all in a chain kind of like this.
So
There's
they're
little
really-
branches.
So they're really large on the molecular scale.
Exactly. And the molecular scale, they're massive.
So
And so you could absolutely have multiple little polar and nonpolar regions. And so at a certain point, it doesn't really become practical to talk about is the whole molecule polar or not. You talk about different regions and what those different regions are doing in a certain scenario. Yeah.
So can they dissolve together and mix together like salt and water?
If it is immersed in a material that has similar regions that can get near each other, then yes, it will dissolve.
So unsaturated fat can't mix in with saturated fat?
Yeah, it can.
It can.
Just because this has some double bonds, that doesn't change the polarity.
Uh-huh.
So saturated and unsaturated, yeah, they would mix. Yeah, because we only care about polarity for that, for the most part. Kind of interesting, okay? So this polarity thing has some more nuance to it than just what we were talking about with the small little molecules that we were looking at, okay? And so I bring this up because this is kind of cool. So because of this polarity situation, what if I had a container full of these fatty acids? Well, one thing that can happen is you get something like this. So this is a simplified representation from the last slide, but it represents the same thing,
Whoa.
right? So here's my carbon, double bonded oxygen, single bonded oxygen, may or may not have a hydrogen there, right? There's those polar bonds from the last slide, and then I have all my carbons going down this chain like this, and then because they're lazy, they don't put the hydrogens, but we all know they're there.
It's giving biology.
It is giving biology. Oh my gosh. Where did you learn about this? Where does this exist? The wall of a cell. What kind of cell?
Human.
Animal cell. This is the cell membrane of an animal cell, which is what you guys are.
Is that the
Oh my gosh, you're made of this.
Is that the stuff that's like real white when you gouge yourself a little too deep when you get yourself cut? Is that like fatty looking stuff?
No.
not at all.
So-
That's
so-
way too small for you to see.
Yes. So fatty acid and fat in your body are not the exact same thing. It's misleading because we kind of use the same term and they are related. You use these and they bond together to make lipids,
And lipids.
and the lipids is the fat that's in your body. So it's different. It's different. It's
Why are
different.
you confusing me over
Similar
here?
but different.
Okay. Okay. So, but anyway, why are these tails naturally being drawn toward each other without us having to do anything about it? They're nonpolar. Yeah, so the nonpolar regions mix mix together well. And then this polar area, especially if there's water, right, in the cytoplasm or outside the cell, is going to be attracted to the water that's just part of our bodies. Okay, so you can get a layer, but you can also get other cool shapes.
Whoa, what is that?
Yeah, you can get a sphere,
Is that?
or you can get like a wall going around, and so you have like a hollow center.
Yeah.
So what are those representing? Like what are those in?
The fatty acid chain.
These are, well, okay, I was gonna ask you. This is your cell membrane. This is the wall of your cells. Okay. I don't, I should know where liposomes, I'm gonna guess that they're in the body, but I don't actually know, so.
They're in the cells.
They're in the cells? Yeah. I mean, I don't know what vacuoles are made of.
I think that's.
I don't know biology.
Suicide sac.
Say what?
No, that's lysosomes.
Geez, suicide attack?
Suicide sac. There's part of a cell that will
Jesus.
essentially kill the entire cell.
Interesting.
Yeah, it's called the suicide sac, or I think it's lysosomes.
Apoptosis.
And the
Yeah.
micelle?
So micelle, these are called micelles. These are something you should use every day. It's in a product that is,
Toothpaste.
okay, micellar water, sure. Anyone know? Play a little hangman. It's a common thing that you should use every day. Soap! There we go.
Ah, there we go.
Okay, maxilla
Oh, yeah, because soap is made of fatty acids.
Right, and there's a reason for that, okay? So,
It separates like the oil.
exactly. Okay, so the grimy stuff on your hand is usually oils, dirt, very non-polar things, very non-polar things. If I run polar water across non-polar stuff on my hands, do you really think they're going to mix together and get washed away down the sink?
No.
Probably not. The water's just going to go over your dirty hands, and maybe you could like physically push some oil and dirt off your hands, but it's only going to be so effective. But what if I had these little micelles mixed in with the water where these things are not bonded together, so just by being moved around they can be jostled around, and little dirt and grime, which is nonpolar, is going to be attracted to those nonpolar tails and then get trapped in the micelles. But what do we know about the outside? Is it polar or nonpolar? It's polar, so it would be attracted to the water and would be very easily picked up by the water.
That's
So when I rinse, all this junk gets carried away. That is how soap works.
Is that why some soap really is not good when you like try to wash your hands? This ain't coming off.
With just water?
No, like because you use some soap when you're like done working on cars and it's like
Right. So yeah, so this is kind of a simplified explanation. There's different, these are called surfactants. There's different surfactants that would be better for different types of oil and grime. And so like obviously, or some of you, I don't know if you're a soap connoisseur, Dawn dish soap is actually better than a lot of other soaps. Like it actually gets grease off. Right. So there's like specific molecules and things that are better for cleaning other things, but
Oh, I could make chicken
The
without
oils
this.
of the water.
so anyway, this whole polarity situation affects a lot of things. Like this is literally your cell membranes and soaps and all kinds of other stuff that I'm not thinking of, but that's important for me. I don't know.
Yeah.
Oh, we're done. Cool.
Yay!
Okay.
Worksheet that I don't have to do.
Okay. All right, let me explain and then I'll let you guys work. This worksheet may look very familiar.
no, don't no.
Remember the worksheet where you had to like build the stuff and I had to sign off on
Oh my
it?
god.
We're not doing that again. Sort of.
So am I by myself?
Okay. What I want you to practice, because I doubt you guys are, some of you are probably good at it, but not all of you. I want you to be able to look at a chemical formula, be able to draw it, be able to tell me what shape it is, and tell me whether it's polar or not. Okay? So I accidentally gave you the worksheet for this like a month early because I forgot it had polarity on it. So I told you to skip that column. Now we can do it. But to make it less boring, I changed some of the molecules, so they're different. Okay, if it helps you to build them, you're welcome to do so. I am not going to require you to build them and me sign off on it.
Or you're requiring us to do it.
Okay, well that's the whole thing. You don't even have to do this because I'm not grading it. So,
Whoa.
but
So crazy.
I'm just saying, no pressure to come build it. If it helps you see the shape to build it, that's great. I've got the stuff up here. If you just want to figure it out on paper, also fair.
Can we just fill out
That's the plan.
polar, non-polar parts?
Yeah, if you actually